You hear glacial outburst flood and you think ice dam breaks, water rushes down. Simple. Wrong. There are mechanisms so varied, so violent, that each one rewrites the valley it carves. Subglacial volcanoes that melt ice kilometers thick in hours. Moraine dams that hold back lakes the size of cities until a single rockfall makes them vanish. Superglacial ponds so small you could miss them on satellite imagery that still drown villages 30 kilometers downstream. Ice dam lakes that drain and refill on a cycle tighter than your mortgage payment. Which ones killed thousands in Peru? Which one emptied a volume twice the size of Lake Erie in days? And which mechanism is accelerating right now as you listen to this? Now it means any catastrophic water release from a glacier, but that single word hides a catastrophe catalog. The 1996 Grimsvötn eruption under Vatnajökull sent melt south. Peak discharge hit 500,000 cubic meters per second. That flow lasted days. Ice chunks weighing 5,000 tons rode the wave. The flood made that river the second largest on Earth by volume for 72 hours, behind only the Amazon. Icebergs 10 meters tall sat stranded on the banks when the water dropped. 185 million tons of silt moved with it. The ring road bridge at Gijuqvezl, a major artery, gone. Tsunami waves 4 meters high, 600 meters wide, tearing across the Sander Plain, all from heat under ice. Also, comment from which city you are hearing this from. This script is researched and factual, using sources from the Icelandic Meteorological Office's Glacial Outburst database, published through 2025 and peer-reviewed findings. In the Journal of Geophysical Research Earth Surface from Roberts and colleagues in 2005, examining Jökulárláp flow physics across multiple glacial settings, with additional verification from USGS flood analysis reports on North American megafloods. Now back to the information. The 1755 eruption melted ice so fast the peak discharge hit somewhere between 200,000 and 400,000 cubic meters per second. Eyewitnesses reported the ground shaking before water emerged. Eyjafjallajökull in 2010, the eruption that shut down European air traffic, also triggered Jökulárláp. Peak flows reached 2,000 to 3,000 cubic meters per second. Smaller than Katla, but still devastating to the ring road and nearby farms, the eastern and western Skafta ice cauldrons under Vatnajökull drain regularly from geothermal heat alone, no eruption needed. These reach peak flows up to 1,800 cubic meters per second, an order of magnitude greater than high summer discharge in those rivers. Water accumulates in a subglacial reservoir. Pressure builds. When hydrostatic pressure exceeds ice overburden pressure, the dam fails. Water carves tunnels through or under the ice. The tunnel enlarges by thermal erosion and mechanical scouring. Flow accelerates. What starts as a trickle becomes a freight train of water, ice, and sediment in hours. The November 1996 event from Grimsvötn took 5 weeks to reach peak after the eruption started. The eruption was 45 kilometers from the ice margin. Water traveled subglacially, melting its own path. Discharge climbed steadily, then spiked. The spike lasted less than a week, but transformed the entire floodplain. Anywhere volcanoes meet glaciers, you get this. The Pacific Northwest of North America, the Andes, Kamchatka, New Zealand. The consequences scale with ice volume and melt rate. But volcanic and geothermal floods are only one type. Glaciers retreat. They leave behind piles of rock, gravel, sand, clay. Moraines. These form natural dams. Lakes fill behind them. Proglacial lakes. The dam is unconsolidated. No cement, no engineering. Just gravity and friction holding back millions of cubic meters of water. Moraine dams are narrow compared to engineered dams. They contain less material. They are steeper, and many have ice cores that melt. Lake Palcacocha in the Cordillera Blanca of Peru. Elevation 4,566 meters. December 13th, 1941. Early morning. A chunk of glacier or an avalanche, reports vary, fell into the lake. Displacement wave. The moraine dam holding back the lake breached. 56 meters deep, that breach. Water, ice, mud, boulders hurtled down the Kojup Valley. Lake Jurkakocha, downstream, was consumed and added to the flow. 15 minutes to reach Huaraz, 23 kilometers away. 400 cubic meters of debris per person in the impact zone. At least 1,800 dead. Some estimates say 4,000. 1/3 of the city destroyed. This was 1941, before modern monitoring, before climate change was a household term. The glacier above it, Palcaraju, has retreated due to warming. The basin fills. Huaraz now has 120,000 people. 22,500 live in the flood path within 80 minutes of an outburst. Studies published in Nature Geoscience in February 2021 found it virtually certain, greater than 99% probability, that human-induced climate change caused the glacier retreat that expanded the lake. The 1941 disaster was one of the earliest identified fatal impacts of anthropogenic climate change. Engineers installed drainage pipes in 2011. They lowered the lake by 3 meters, not 15 meters as planned. Funding issues. The threat persists. Calving from a glacier terminus. The wave overtops the dam. Water erodes the crest. Erosion accelerates. Positive feedback. The breach grows. Flow increases. Within hours, the dam is gone. Piping is internal erosion. Water seeps through the porous moraine. It carves tunnels. The tunnels enlarge. Eventually, the dam fails from within. Structural collapse happens when the moraine itself becomes unstable. Ice core melt. Seismic shaking. Saturation. The dam slumps. Water escapes. They found dam height and lake volume are the most sensitive parameters for peak discharge. A model validated against the Tangjiashan Lake outburst in China showed good agreement. The South Lonak Glacial Lake in Sikkim, India, was modeled. October 4th, 2023, it burst. Peak discharge estimates vary, but the flood killed at least 55 people and destroyed the 1,200 megawatt Chungthang Dam downstream. The lake covered 1.66 square kilometers. Big, visible, monitored, it's still breached. The moraine lake will produce roughly 10 times the peak flow. Why? Moraine dams fail catastrophically and completely. Ice dams can fail partially, regulate flow, reseal. Moraine dams do not regenerate. Once gone, they stay gone. Ice can refreeze. Ice dams allow cyclic floods. Moraine dams give you one shot. July 8th, 2025. The Botekoshi River along the Nepal-China border. Flash flood. At least 9 dead in Rasuagati village. Dozens missing. The bridge connecting Nepal to China gone. The source? A superglacial lake on the Purapu Glacier at 5,150 meters elevation, 36 kilometers upstream. Satellite imagery from ICIMOD, the International Center for Integrated Mountain Development, showed the lake appeared as a small pond in March 2025. By June, it had expanded significantly. Then it drained. The flood traveled over 100 kilometers. Sediment-laden, boulders, debris. Tame village in Solukhumbu, Nepal. Flood from Thianbo Glacial Lake. Lake size, 0.05 square kilometers. Tiny. It destroyed homes, hotels, schools, health posts. 135 residents displaced. May 2025. Tilgaon village in Humla district, Nepal. 2 glacial lakes burst. Infrastructure destroyed. July 2025. Upper Mustang, central Nepal. Ice-dammed lake, 0.016 square kilometers. Flood rushed 35 kilometers downstream. 4 bridges destroyed. They form in debris-covered glacier regions where ablation accelerates around superglacial ponds. Thermal undercutting, ice cliff development. These lakes drain through moulins, crevasses, and glacial tunnels. The drainage can be sudden. The volume may be small, but the discharge rate is high, and they form at high elevation. Gravitational potential energy. By the time the water reaches valleys, it has entrained massive amounts of sediment and debris. Momentum multiplies. Research published in Natural Hazards and Earth System Sciences in July 2024 by Wangchuk and Subaki modeled a breach of Thorthmi Glacial Lake in Bhutan, using the breach and HEC-RAS models. Peak discharge, 16,360 cubic meters per second within 4 hours of breach, 245 hectares of agricultural land at risk. Past events in Bhutan include the October 1994 Luggi Lake outburst, 21 dead, massive downstream destruction. The most recent Lemthang Cho outburst was July 28, 2015. The June 2025 Botekoshi flood in Nepal was attributed by ICIMOD to draining of a superglacial ice-dammed lake that grew rapidly between December 2024 and June 2025. Researchers called the acceleration of these events completely unprecedented. Frequency has increased threefold compared to projections for the end of the 21st century. We hit the future early. Glaciers advance, they block valleys. Rivers back up, lakes form. Ice is the dam. The dam can float. When water pressure exceeds ice overburden pressure, the dam lifts off the bed. Water escapes beneath. Lake drains. Ice settles. Lake refills. Cycle repeats. Lake George near the Nick River in Alaska. Large annual outbreaks from 1918 to 1966, every single year. Then the Nick Glacier retreated. Ice dam no longer forms. Flood stopped. Might resume if the glacier thickens. Suicide Basin on Mendenhall Glacier in Juneau. Floods nearly every year since 2011. August 6th, 2024. Water surged to 15.99 feet, past the previous record of 14.92. Homes flooded, evacuations, property damage. The cause? Decline of Mendenhall Glacier over 2 decades created the unstable basin. Despite more frequent events at specific sites like Suicide Basin, statewide frequency of ice-dammed lake outbursts in Alaska has not changed since 1985. The amount of water and peak discharge have decreased over time. Glaciers are thinning, dams are weaker, lakes are smaller. Or the ice floats, or water overspills and erodes a breach. Lago Cache Dos in Patagonia, dammed by Colonia Glacier, drained at least 21 times in 10 years. Subglacial tunnels beneath the ice, every time it refills and drains again. Each event impacts downstream communities, infrastructure, salmon spawning beds, sediment scour, tourism economy. Superglacial lakes drain vertically through hydrofractures. Studies in Greenland on Nyogalvirdsbrien, the 79 degrees north glacier, used radar and UAV surveys. A superglacial lake, volume up to 123 million cubic meters. Extensive fracture fields form, vertical displacement across fracture faces, triangular-shaped moulins, apertures tens of meters wide. Water flows into these even weeks after main drainage. Sometimes water level rises and overflows. These fractures reactivate in subsequent years. Ice-penetrating radar shows three-dimensional and glacial features originating from drainage. These features change over years but remain detectable even years after formation. Water pressure propagates the fracture downward. Hydrofracture. The water exploits weaknesses in the ice. The fracture reaches the bed or an in-glacial conduit. Drainage initiates. Flow enlarges the conduit by thermal and mechanical erosion. The lake empties in hours to days, in some cases gradual, in others catastrophic. The resulting flood delivers vast amounts of water to the ice sheet base, impacts glacier velocity, lifts the ice, accelerates flow, affects sea level contribution. Greenland ice sheet. Superglacial lake drainage events are increasing. Hundreds of lakes drain every summer, some slowly, some in hours. The water reaches the bed. Lubrication, speed up events, but not all lakes drain, some freeze. Some fill and remain. Predicting which lakes will drain is a challenge. Basin shape, ice thickness, crevasse density, water temperature, pressure threshold. Researchers use models, but the system is chaotic. Glacial Lake Missoula, late Pleistocene. Between 20,000 and 13,000 years ago, the Purcell Trench lobe of the Cordilleran ice sheet dammed the Clark Fork River in northwestern Montana. Ice dam over 1 kilometer thick. Water backed up. Lake Missoula. Volume, 2,200 cubic kilometers, greater than Lake Erie and Lake Ontario combined. No outlet. Water rose. At around 1,100 feet depth, hydrostatic pressure lifted the ice dam. Catastrophic failure. That is 50 to 100 times the average discharge of the Amazon River. Flow speed approached 130 kilometers per hour. A wall of water 2,000 feet high surged through the breach. The flood drained Lake Missoula in days. Then the ice reformed, lake refilled. Average cycle, 55 years. This repeated dozens of times, at least 25 massive floods, maybe as many as 89. More than 25 floods had peak discharges exceeding 1 million cubic meters per second. At least 6 or 7 exceeded 6.5 million cubic meters per second. One flood topped 10 million cubic meters per second. The floods carved the channeled scablands of eastern Washington. 30,000 square kilometers of coulees, cataracts, scour marks, boulder bars, ice-rafted erratics. J. Harlan Bretz proposed this in the 1920s. The establishment rejected it. Uniformitarianism ruled, no catastrophes. Bretz had the receipts. By the 1950s, consensus shifted. The evidence was overwhelming. Erosion rates during the floods were extreme. The November 1996 Iceland Jökulhlaup, with peak discharge 45 to 53,000 cubic meters per second, moved 2-meter diameter boulders in suspension. Stream power, 40,000 watts per square meter. Missoula floods. Stream power at some locations hit 100,000 to 1 million watts per square meter. Landscape scale transformation in days. The gap could only transmit 20% of peak discharge. Water backed up. Temporary Lake Lewis formed in the Pasco Basin. When the gap cleared, water rushed through the Columbia River Gorge. Flood depths in the gorge exceeded 215 meters based on high water marks on surrounding ridges. The town of Lisle, Washington, sits on a giant eddy bar left by the floods. Slackwater deposits in the Yakima and Walla Walla valleys show layered silt separated by thin soil horizons. Each layer is one flood. Ash layers in the soils help with timing. Mount St. Helens. Set Estefra is 13,000 years old. Many Missoula floods post-date that eruption. Indigenous North American flood stories describe catastrophic waters. The Kalapuya people tell of Atswin, oral histories passed down for millennia, first-hand witnesses of the megafloods. Pluvial Lake in the eastern Great Basin, Pleistocene predecessor to Great Salt Lake. During the last glacial, the basin filled. Over 50,000 square kilometers covered, 10,400 cubic kilometers of water. Maximum stage reached Red Rock Pass, the lowest divide to the Snake River Basin north. The lake overtopped, rapid incision. 108 to 125 meters cut into the outlet. Half the lake volume spilled. Total volume, about twice that of a maximum Missoula flood. But peak discharge was only 1 million cubic meters per second, 1/10 of the largest Missoula floods. Why? Steadier flow, simpler path. The Bonneville flood was singular. About 18,000 years ago, no evidence of multiple events. It entered the Columbia system from the southeast. The comparison teaches us that flood magnitude is not just about volume, it is about release rate, breach geometry, flow path. Constrictions, energy dissipation, outburst floods. More than half live in just 4 countries. India, Pakistan, Peru, China. High Mountains Asia has the highest exposure. On average, 1 million people live within 10 kilometers of a glacial lake. In the Cordillera Blanca of Peru alone, over 30 glacier disasters have killed nearly 30,000 people since 1941. Pakistan has over 7,000 glaciers. More than 3,000 glacial lakes in Gilgit-Baltistan as of 2018. 30 identified by UNDP as posing imminent threat. In Bhutan, 24 out of 2,674 glacial lakes identified as candidates for future outbursts. Nepal has 21 potentially dangerous glacial lakes, but only 2 functioning early warning systems, Imja and Cho Rolpa. Thousands of other lakes, including short-lived superglacial ones, remain unmonitored. Himalayan glaciers have lost mass at accelerating rates, equilibrium line altitude rising, glaciers retreating, lakes forming and expanding. Between 1990 and 2025, the number and size of glacial lakes increased rapidly. Cho Rolpa in the Roll Wailing Valley, Nepal, altitude 4,580 meters, dammed by a 150-meter-high unconsolidated terminal moraine. The lake is growing every year due to Tricarding Glacier retreat. Largest and most dangerous glacial lake in Nepal, 90 to 100 million cubic meters stored. Modeling published in Proceedings of the International Association of Hydrological Sciences in November 2024 estimated peak flows from a 20-meter breach at 8,198 cubic meters per second. From a 40-meter breach, 26,662 cubic meters per second. Travel time to populated areas allows for early warning. But landslides or debris dams could create ponding. Community-based early warning systems are needed. They exist in some places, not everywhere. Factors include dam type, lake volume, freeboard, slope stability around the lake, distance to glacier terminus, glacier calving rate, earthquake frequency, permafrost degradation, precipitation patterns. A study published in April 2024 in phys.org by Wood and colleagues challenged assumptions. Earthquakes are often blamed for triggering outbursts. The team analyzed 11,733 earthquakes magnitude 4 or greater since 1900, 67 temporally known glacial lake outbursts in the same period. They found only 11 outbursts could be confidently linked to earthquakes, 6 of those tied to a single magnitude 7.9 earthquake in May 1970 in the Cordillera Blanca, Peru. That event destabilized mostly moraine-dammed lakes. The researchers concluded earthquakes may not be the primary driver. Permafrost degradation and structural geology may matter more. Warming temperatures destabilize slopes. Thawing permafrost removes the glue holding rock faces together. Rock and ice avalanches increase. These avalanches displace water. Overtopping follows. When it does, a Jokul Alps will follow. Myrtle's Jokul covers the volcano. Peak discharge could rival or exceed past events. 200,000 cubic meters per second or more. The ring road, farms, infrastructure all at risk. Monitoring is constant. Seismometers, GPS, gas sensors. Glaciologists and volcanologists watch. When activity spikes, evacuation windows are narrow, hours at best. Half of all glaciers could be gone by the end of this century, even if aggressive climate targets are met. Research by Rounce and colleagues found this. As glaciers shrink, some hazards decrease. Smaller ice dams, less water stored. But new hazards emerge. More lakes forming, lakes in unstable locations, slopes destabilizing, permafrost thawing. The transition period is dangerous. Lakes are growing faster than infrastructure and monitoring can adapt. In Alaska, despite glacier thinning, ice-dammed lakes persist. They will until glaciers retreat entirely or stabilize. Ski Lac Lake on the Kenai River, Hidden Lake on the Kennecott River, Snow Lake near Seward, all present threats to communities. Even small outbursts can be destructive when they occur near settlements. Loss of life, property damage, loss of power, ecological impacts. Salmon spawning can be disrupted by stream bed scour during floods. Sediment loads alter fish habitat. Tourism economies depend on fisheries. Floods impact all of it. Hydropower stations, roads, bridges, agricultural land, water supply. The 2010 flood from Lake 513 in the Cordillera Blanca, Peru, resulted from a massive rockfall. The rockfall was linked to warming and permafrost thaw at altitude. Slopes that were stable for centuries are failing now. Seismic monitoring, hydrological modeling, the breach model, HEC-RAS, ANUGA for two-dimensional shallow water simulations, glaciostatic adjustment models, all tools to predict, to understand, to mitigate, but models need data. Data needs funding. Funding needs political will. Engineers like Cesar Portocarrero Rodriguez pioneered these techniques, export them globally. Nepal partners with UNDP and ICMOD, early warning systems, community preparedness, infrastructure reinforcement, but efforts are patchwork. Many lakes unmonitored, many communities unaware. The case hinges on establishing a direct link between the company's emissions and the increased flood hazard from Lake Palcacocha. Evidence from the Nature Geoscience study in 2021 showing 99% probability of human-caused. Glacier retreat bolsters the claim. The case is ongoing. If successful, it sets precedent. Emitters liable for climate impacts. Other cases may follow. The International Court of Justice has established that nations have duties regarding environmental impacts on other countries. International Tribunal for the Law of the Sea issued advisory opinion on climate obligations. Frameworks exist. Enforcement is the battle. Ice dams floating and releasing cyclic floods, and glacial networks reactivating yearly, megafloods that carved continents. Each mechanism has signatures, each leaves evidence, sediment assemblages, erosional features, high water marks, layered deposits, boulder bars, ice-rafted erratics, scour channels, dry waterfalls. Quantitative flow analyses at Wallula Gap and Columbia Gorge placed peak discharge at 5 to 15 million cubic meters per second through constrictions. Hydraulic modeling raised questions about canyon erosion rates and possible additional water sources. Glacial Lake Columbia, impounded by the Okanogan Lobe, lasted 2,000 to 5,000 years between about 18.5 and 15,000. Years ago, Missoula floods entering that lake were diverted into eastern Washington coulees and scablin tracts. Routes changed as ice lobes advanced and retreated. Moses Coulee took at least 4 floods. Then, the Okanogan Lobe blocked it. Grand Coulee opened. Telford Crab Creek and Cheney Palouse scablin tracts. Flow paths shifted. Erosion deepened. The landscape we see is a palimpsest. Multiple floods, multiple routes, layer on layer. Quaternary outbursts, flood powers of 100,000 to 1 million watts per square meter over large areas. Giant paleofloods, the Yarlung Changpo in Tibet. Repeated megafloods in the late Pleistocene and Holocene. Peak discharges 500,000 to 1.1 million cubic meters per second, 5 to 10 times greater than the 2000 Yigong flood with peak of 95,000 cubic meters per second. 20 to 40 times greater than the 2018 Sedongpu flood at 25,000 cubic meters per second. Evidence in slackwater deposits and gravel bars, radiocarbon ages, glacial moraine ages, lake sediment stratigraphy. We know these events happened. We know their scale. We do not know all the triggers. Over 44 flood-related turbidite beds between 19.3 and 14.9 thousand years ago. Periodicity, 50 to 80 years. Each Missoula outburst sent fresh water and sediment into the ocean. Deep-sea deposits totaling around 1,450 cubic kilometers. Freshwater pulses influenced North Pacific circulation. Sustained freshening and cooling from 19.0 to 16.5 thousand years ago. Glacial outburst floods affect climate. They alter ocean salinity, thermohaline circulation, regional climate patterns. These are not local events. They ripple globally. Some drain episodically. Willen's ice stream, subglacial lake. Willen's drains into the ocean, volume uncertain, timing unpredictable. West Antarctic ice sheet is vulnerable, marine-based, grounded below sea level. Warm ocean water intrudes beneath ice shelves, melting accelerates. Subglacial lakes may play a role in ice sheet stability. Water at the base lubricates, ice flows faster. If drainage changes, dynamics change. Sea level rise accelerates. We monitor. We model. Uncertainty persists. Moraine dams grow and breach. Climate warms. Glaciers thin. Lakes expand. New lakes form. Permafrost thaws. Slopes fail. Avalanches occur. Displacement waves overtop dams. Dams breach. Floods begin. Sediment mobilizes. Boulders move. Infrastructure is destroyed. Lives are lost. Survivors adapt. Engineers install drains. Governments fund monitoring. Scientists model. The cycle continues. A child walking to school. A family in a valley who hear a sound like a freight train and have minutes. Early warning systems by time, sirens, automated sensors, satellite triggers, cell phone alerts, community drills, evacuation routes, shelters. All of this costs money. Developed nations have resources. Developing nations where the threat is highest often do not. Climate finance, loss and damage fund under UNFCCC, promises made, delivery slow. Youth in affected regions do not see glacial lake outburst floods as a distant future problem. It is a present danger. Tem Village in 2024, Rasuagadi in 2025. These are this decade, this year. The acceleration shocks experts. ICIMOD researchers describe it as completely unprecedented in the Hindu Kush Himalayan region. Threefold increase compared to end-of-century projections. We crossed a threshold. The new normal is more frequent, more widespread, more deadly. Thermal imaging for glacier surface melt. Hydrodynamic modeling with Anuga software, accounting for glacial isostatic adjustment, erosion and deposition, sediment bulking, lahars, where volcanic ash mixes with water, debris flows. Hyperconcentrated flows. Flow classification depends on sediment to water ratio. Glacial outburst floods can transition from water-dominated to sediment-dominated as they entrain material downstream. This changes velocity, changes destructiveness, changes depositional patterns. Degradation rate, hazard assessment, resources for remediation can be allocated. Every measurement narrows uncertainty. Every dataset improves models. Every model informs decisions. Superglacial lakes that form too fast to map. Earthquakes that strike without warning. Volcanic eruptions with minimal precursors. Landslides from thawing permafrost in zones thought stable. Climate change introduces non-stationarity. Historical patterns no longer predict future behavior. We adapt, we learn, we iterate. Glacier de la Plaine Morte in the Swiss Alps. Lac des Faverges, drained annually as a glacier lake outburst flood since 2011. 2018. Lake volume exceeded 2 million cubic meters. Flood caused downstream damage. 2019, authorities dug a superglacial channel. Artificially initiated drainage. Peak discharge reduced by over 90% compared to 2018. Success, but each lake is unique. Topography, ice dynamics, resources. Feasibility varies. Not every lake can be drained safely. Some are too large, too remote, too unstable. Intervention itself carries risk. Valunaraju Glacier in the Cordillera Blanca, Peru. Rock falls into a new glacial lake. Debris flow down the Casca River Valley. Reached Huaraz. Multiple deaths. Dozens of homes destroyed. NASA Earth Observatory published imagery May 7, 2025. Landsat 8 OLE. Rocky debris and brown sediment blanket the valley. One lake near Glacier Terminus appears drained. Climbers reported consistent rockfall all morning. At 3:30 a.m., slide as loud as freight train. The glacier has thinned and receded for decades. New lakes perched on icy slopes. One burst, high altitude, gravitational energy. By the time it reached the city, momentum was catastrophic. Another entry in the catalog, another village grieving. Glacial Lake Missoula, multiple times. Which mechanism is accelerating? All of them. Volcanic Jökulhlaups in Iceland happen on geologic timescales, eruptions every few decades. But human populations near floodplains grow. Exposure increases. Moraine-dammed lake outbursts occur more frequently as climate warms. Glaciers retreat, lakes expand, dams weaken. Superglacial lake drainage accelerates. More lakes forming. Faster growth, shorter lifespans before drainage. Ice dam lake cycles intensify in some regions due to glacier thinning. And glacial systems evolve. Fracture networks reactivate. And the ancient megafloods? Those required ice sheets. We don't have those now, not yet. But Antarctic and Greenland subglacial systems? Active, changing, poorly understood. 3.5 miles wide, 400 feet high. Dry now. During Missoula floods, it was Niagara times 10. The power that carved it is unimaginable standing there today. But the geomorphology does not lie. Scour marks, streamlined obstacles. Longitudinal grooves, giant current ripples and gravel bars. Erratics, rocks, carried hundreds of kilometers by icebergs floating on floodwater. Dropped when ice melted. Touche beds, rhythmites, each couplet of silt and sand one flood. Count them. Dozens, separated by soil horizons where vegetation grew between floods. Time enough for a forest to start, then erased. The bridge was designed for a river, not for a river that becomes the second largest on Earth for 3 days. The ruins teach humility. Engineering can be overmatched. Nature at catastrophic scale does not negotiate. In Peru, you can walk the Cojup Valley. The breach at Lake Palcacocha moraine is still there, 56 meters deep. Vegetation has returned, but the scar is visible. Juarez rebuilt. The city is larger now, more people in the path. The lake above is larger too. The equation worsens on both sides. Engineers did what they could. 3 meters of drainage. It's something, not enough. The next slide, the next displacement wave, is a matter of when. In Nepal, you can trek to Imja Lake, see the drainage infrastructure, pipes, channels, early warning sensors. Then look at the hundreds of other lakes in the valley, unmonitored, growing, invisible to all but satellites and the people who live below. Glacial outburst floods are extreme hydrology. Each type, each mechanism, each trigger writes its own disaster. But they share common threads: ice, water, gravity, energy, pressure, time, and increasingly human fingerprints. Warming that started in the industrial era created conditions that did not exist before. Glaciers that were stable for millennia now retreat. Lakes that did not exist in 1850 now hold enough water to drown cities. Permafrost that glued mountains together for 10,000 years now thaws in summer. Avalanches that were rare now happen annually. We forgot, or never knew, that the landscape was shaped by catastrophes. The geology remembers. The sediment layers, the erosional features, the boulders too big to move by any river we have seen. Except we have seen them. In 1996, in Iceland. In the Pleistocene across Washington. In 2023 in Sikkim. In 2025 in Nepal and Peru. We see them now. We just did not predict them. The challenge ahead is prediction, mitigation, adaptation. We can monitor lakes, we can model breaches, we can engineer drainage, we can build early warning systems, we can relocate communities. But none of this is cheap. None of it is easy. None of it is guaranteed. A model is only as good as its inputs. A sensor is only as reliable as its maintenance. An evacuation route is only effective if people use it, and funding is always the constraint. That number grows, glaciers retreat, lakes expand, populations increase, exposure multiplies, vulnerability depends on resources. Wealthier nations can invest, poorer nations cannot. The inequity is stark. The nations least responsible for emissions face the greatest risk. The nations most responsible have the resources to adapt. Climate justice is not abstract. It is measured in lives saved or lost when the dam breaks. The future holds more glacial outburst floods, not fewer. Not until glaciers stabilize or disappear entirely. Transition takes centuries. We are in the peak danger window. Maximum lake formation, maximum instability. Minimum preparedness in many regions. We close the gap or people die. Simple. Moraine dam failures. Assess dam integrity, drain unstable lakes, reinforce dams, relocate populations. Superglacial lake drainage. Map lakes with high-resolution satellites, model potential impacts, establish evacuation protocols. Ice dam floods. Monitor ice dam stability, predict flotation thresholds, regulate downstream development. In glacial drainage, understand fracture mechanics, predict drainage timing, manage glacier velocity changes. Megafloods. Study the past to understand what is possible. Use the knowledge to assess modern risks. Antarctic subglacial lake drainage could destabilize ice sheets. Sea level rise affects billions. The stakes are existential. We do not close with hope or despair. We close with evidence. In 2018, researchers drilling near Grimsvatn volcano in Iceland accidentally triggered a Jökulhlaup from a subglacial lake. The borehole breached the ice seal. Water escaped. Peak flow was orders of magnitude less than an eruption-triggered event, but it proved the mechanism. Hydrofracturing. Flooding of moulins by precipitation can also trigger Jökulhlaups naturally. The system is sensitive. Small perturbations can cascade. Future archaeologists will find our cities buried the same way, unless we act, unless we fund monitoring, unless we engineer solutions, unless we reduce emissions and slow the warming that drives glacier retreat. Every tenth of a degree matters. Every lake monitored matters. Every early warning system matters. Every person evacuated is a life saved. Grimsvatn 500,000 cubic meters per second. Palcacocha 1,800 dead. Missoula 20 million cubic meters per second. 15 million people at risk today. Thiambo Lake 0.05 square kilometers, still catastrophic. The receipts are in. The data is clear. The future is written in the moraines, the sediment, the fractured ice. Read it.